Okay. So we are going to start with atomic structure today. Okay. So when we talk about atoms, so atoms have three subatomic particles in it, which are protons, electrons, and neutrons. So protons and electrons, it is present in nucleus. It is also present in nucleus, and this is present in shells. And all of the three are called subatomic particles. Okay. Now, जो हम the charge we talk about is basically their relative charge or their relative mass. So for example, we have these three particles. One is proton, second one is neutron, and third one is electron, right? So we have their relative charge, and you must know their relative mass as well. These are not their actual mass or the actual charge. So the relative charge for proton is +1, neutron have no charge, and electron has -1 charge. That is again its relative charge, not the actual charge. And in the same way, the relative mass of proton is 1, the relative mass of neutron is 1, and the relative mass of electron is 1/1836, which means that the mass of electron is 1836 times smaller than the mass of uh, proton. Is this understandable, Alishma?
Yes, sir.
Okay. Now, what is the unit of a charge? Yes, Alishma, do you
It's
know that?
AMU.
I'm talking about the actual unit of charge. Not mass. It's Coulomb.
Coulomb, yes.
Okay. And for example, if we are going to take the actual mass, so usually we record the mass in grams or you know uh, milligrams or in kgs, right?
Yes.
Okay. So proton. Okay, these actual masses and charges, there is no need to remember. There is no need to memorize them because if it is needed, examiner is going to provide you the actual charge and the actual mass of proton and of these proton, electron, and neutron. So the actual charge of proton is +1.6 exponent -19 Coulomb. For electron, it is -1.6 exponent -19 Coulomb. and it has again nil, no charge. And when we talk about mass, the mass of proton and neutron are exactly same, which is 1.67 exponent minus 24 grams. So see, it's very small in gram, exponent minus 24, but both have exactly same mass. So when we simplify it, we will get the ratio of 1:1. That's why we suggested the relative mass of proton and neutron is 1 and 1. Is this understandable?
Yes, sir.
Okay. And over here, it is 9.10 exponent minus 28 gram. Okay. Now, next thing that I needed to discuss is splitting of, okay, as I'm just going to show you the electronic configurations, we will not spend much time on it. If you have any issue, you can ask, otherwise we will move to the shapes, okay?
Okay, sir.
Particles in applied electric field. So here we has the applied electric field. This is positive, this is negative. And here we have the source of atoms from where we bombard the atoms. So the beam of that atoms passes through the electric field. So as it reaches the electric field, what happens that some particles splits and deflected towards the negative plate. Some particles deflect towards the positive plate. And some particles move to straight. So if you see, we can conclude the particles which moves in a straight direction and does not influenced by any field are
Electrons.
protons. These are neutral particles, right? So that's why we call it neutrons, not protons. Sorry, my bad. Okay. And the one which deflected towards the negative field must be positive one, right?
Yes.
And if they are positive, so that's why we consider them protons. Okay. And the one which deflected towards the positive plate must be the negative. And that's why they are considered as
Electrons.
electrons. Is this understandable?
Yes, sir.
Okay. Now, here another important thing which you have to focus is the angle of deflection towards the negative plate and the angle of deflection towards the positive plate. Are they equal?
No, they're not,
They are not.
because electron has less mass, so it will be deflected more, while proton has mass of one, relative mass of one,
Proton's
so it
mass is
will
greater,
deflected
right?
less.
But it's not just the mass. Although you are right, but it's not just the mass. So you have to remember this whenever if the examiner asks you to draw this diagram, so you must remember this, that the angle of deflection of,
Equal charge over mass.
yeah, charge over mass. Electron, very good, must be greater than angle of deflection of proton. Is this understandable?
Yes, sir.
Okay. Hmm. Now I have a one question for you. Here is the question. Now, in this question, if you choose A is the correct answer, it means you are assuming that first, second, and third, all the statements are correct. And if you're choosing B, so it means one and two statement are correct. And if you're choosing C, then it means second and third statement are correct. And if you're choosing C, B, it means one only correct. So can you try to attempt this?
Yes, sir. Is the answer D?
Uh, you are saying B for ball.
I'm saying, are these numbers that are written?
See,
Only one of them, two of them.
here you is 1, 2, and 3. These are the three particles.
Yes. Mhm.
So particle Y compose, you have to identify the composition of particle Y. If you choose A as a correct option, then it means that particle Y has a composition which is provided in a statement 1, 2, and 3. Now, did you understand?
Yes. The answer is C, 2 and 3.
Okay. You are saying answer is C, 2, and 3.
Yes.
Okay. But the correct answer is actually B, not C. Now let's have a look. See, beams of charged particles are deflected by an electrical field. In identical conditions, the angle of deflection of particle is proportional to its charge to mass ratio. So what they are saying that if the conditions are identical and you are not changing the condition, then the angle of deflection is depends upon or is proportional to charge to mass ratio, right?
Yes.
Now, in an experiment, proton are deflected by an angle of positive 15. So they have given you the angle of deflection of proton that it deflects to positive 15 degrees. Is this clear?
Yes, sir.
Okay. In another experiment, under identical conditions, particle Y is deflected by an angle of minus 5 degree. So it means if this is minus 15, if this is positive 15 degrees, so it could be minus 5, for example, right?
Yes, sir.
So from this, I'm sure that this particle Y must be negatively charged, isn't it?
Yes,
Because
sir.
if it is positively charged, then its angle of deflection must be positive. Did you understand this?
Yes, sir.
Okay. Now, if I work on the charges of these, so this is positive 1 and negative 2, positive 3 and negative 5, positive 4 and negative 1. So the net charge of the particle 1 is going to be minus 1. The net charge of particle 2 is going to be minus 2. And the net charge of particle 3 is going to be positive 3. Is this understandable?
Yes, sir.
So 3 goes wrong, isn't it?
Yes.
If you have any query till here, you can ask.
No, sir.
Okay. Now, charge to mass ratio and angle. What is the charge to mass ratio of proton? Proton's charge, what is the charge of proton? Positive 1.
Yes, sir.
What is the charge of mass of proton? 1.
1.
And what is the angle of deflection?
Positive 15.
Positive 15. Now, let's work for particle 1, the charge to mass ratio. What is the charge of particle 1?
Negative 1.
Negative 1. What is the mass of particle 1?
3.
3. Okay, what is the mass of particle 2?
6.
6. Okay. So I know its charge to mass ratio, but I don't know its angle of deflection, isn't it?
Yes, sir.
But I take the ratio that if the charge to mass ratio is positive 1, then the angle of deflection is positive 15.
Yes.
Now, if you calculate the x,
Cross multiply.
it is, yeah, cross multiply, you will get the value of x.
It's negative 5.
Negative 5. See, is it justified?
Yes, sir.
So it means statement 1 is correct. Now, statement 2, the charge to mass ratio, charge is -2 and the mass is 6, right?
Which again goes to minus 1
Minus
over
1
3
into
if we
3, so it means
simplify it.
I'm again going to get the angle of deflection of negative 5.
Yes, sir.
So 1 and 2 is correct, which means B is the correct answer. I hope it's clear to you now.
Yes, sir.
Okay. Okay. This is what we have discussed in the last class, right?
Yes, sir. Yes.
Okay. Now, I'm going to discuss the shapes of orbitals. S is spherical in shape, and P is dumbbell shape. Okay.
Yes, sir.
Now, if examiner asks you to draw them, so what examiners do? Mostly examiner provides you the axis. Okay. So S is a spherical, so you always draw a circle in the origin, that is S. Okay.
Yes, sir.
And for a dumbbell, it's there are three p orbitals. One is px, one is py, and one is pz. Okay. So px is drawn on x-axis, two lobes like this. For py, we draw two lobes like this, equal lobes. And on pz, we draw two lobes like this. Is this clear?
Yes, sir.
Okay. Now, uh, we are going to discuss the, okay, you know how to fill the orbitals as well, right?
Yes.
Yes or not?
Yes, sir.
Okay. So I want you to just write the electronic configuration for chromium, which is 24, and copper, which is 29, and just give me 3 to 4 minutes. I will be back from the restroom. Okay.
Yes, sir.
Thank you. Yes, Alishba, are you done?
Yes, sir.
So can you tell me the configuration, both of the configurations?
Yes, sir. For chromium, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5.
Very good. So
And for
chromium, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5, right?
yes, sir.
For copper,
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9.
3s2, 3p6, 4s1, 3d10. It's also going to be same like this. Okay?
Yes, sir.
Okay. So I'm going to this whole file with you. So you can go through with the questions and complete notes in detail. And if you find any difficulty in any one of them, you can ask me. Okay. So basically the difference is due to this. See, this is the thing that the energy of 4s is lower and 3d is higher. So whenever we fill the electrons, see, that's why after 3p, always 4s gets filled, and after 4s 3d gets filled. And it is because the reason that 4s at a lower energy than 3d. But as soon as the get filled, 4s goes to the higher energy and 3d comes to the lower energy. Is this understandable?
Yes, sir.
And that's why when we remove the electron from the transition element, see, in transition element we always fill the 4s first, right? And then 3d.
Yes, sir.
So when we remove the electrons, when we are writing the electronic configuration of their cations, we remove the electrons initially from 4s only. And if we have to remove further more electrons, then the electron would be removed from 3d. Is this clear?
Yes, sir.
Okay. Now, uh, so this is the reason over here that chromium is becoming 4s1 3d5 and 4s1 3d2 because they become more stable than this configuration. So to attain the stability, the electron from 4s jumps to 3d, and as a result, the electronic configuration of these two elements are not as normal or as simple as the rest of the elements. So this is the stability rule, that if the completely filled orbital like S has 2 electron, P has 6 electron, and D has 10 electrons, then it is completely filled, it's most stable. And if they are half filled, like S has 1 electron, P has 3 electron, and D has 5 electron, then it is half filled, which is moderately stable. And partially stable, S has no partially stable situation, either it is half filled or completely filled or vacant. P has a partially filled these situations and D has a partially filled these situations, and in all of these, it is considered as least stable. Is this clear?
Yes, sir.
Okay. So that is the pairing of electron. We know that electrons have a two type of movements. One is around the nucleus and there is a spinning on its own axis. That's why whenever electron is moving around the nucleus, it is moving like this. It is not moving like this, okay?
Yes, sir.
Okay. So the spinning can be of two types. Either the electron is spinning clockwise or anti-clockwise. Okay.
Yes, sir.
So if there are two electrons which are spinning clockwise or which are spinning anti-clockwise, we can represent them like this. It means that both have a same spin. And if I represent electrons with the up directions opposite to each other, it means that Okay. Sorry, they have
If
opposite.
both are the same.
If they have a same spins, then they can be represented like this or this. And if I make them like this, then it means they has a opposite spin. And due to the opposite
Yes, sir.
spin, what happens? Their repulsion, because both are electrons are negatively charged, right?
Yes, sir.
So their due to the opposite spin, their repulsion is minimized, and that's why they become pair. Because the electrons with the same spin, they are not going to pair with each other. They are not going to pair with each other because the repulsion between them is maximum. But here, due to the opposite spin, their repulsion is minimized, and that's why they paired up. Is this clear?
Yes, sir.
Okay. So here I did one example for the filling of bromine, orbital filling of bromine. And then I gave the task to the students to fill the rest of the electron elements, the first 30 elements. So you can also try it on your own.
Yes, sir.
Okay. Okay. There is another important thing which is quickly help you to figure out the valence shell electronic configuration, not the whole, but the valence shell electronic configuration. Like you must know that these elements are called S block, these are called D block, these are called P block, and these are F block. Okay. For example, if I open a periodic table in front of you, no, it's not.
S has all the metals. P has all the transitions.
No, D
D
has
has all
only
the
transition,
gases.
but transition are also metals, isn't it?
Yes, sir.
Okay, let me ask you one thing. For example, if the periodic table is like this in front of you, and I ask you the electronic configuration of this tellurium, that where the tellurium electronic configuration will end, can you tell me?
Um,
The shortcut way.
what is the shortcut for?
The shortcut way is C, 1, 2, 3, 4, 5. It's in the fifth row.
Yes, sir.
So it's 5. It is P block, right? It's P1,
Yes, sir.
2, P3, P4. So here tellurium is going to end. 5P4.
Okay.
See, for example, barium. So these two are S block, right?
Yes, sir.
So this is going to be
6s2.
yeah, 6s2. Like chlorine. So 3p5. Is it understandable?
Yes, sir.
Okay. But here in this region, this thing becomes a little complicated. For example, if I took iron, so you will start 1, 2, 3, 4. And if you recall, it's not 4, it's 5, right? Because the
Yes.
electron is shifted. Then 6, 7, 8. No, sorry. It is also 5. Then 6, 7, 8, 10, and 10. So for example, if I have to write its electronic configuration as it's 3, so and its number is 4, right? So it is going to be 4s2, but the D subshell is always of the previous number. So it is going to be 3d3. For example, if I took nickel, so it is going to be 4s2, 3d8. If I'm going to take copper or cobalt, 4s2, 3d7. Is this understandable?
Yes, sir.
Okay, just give me a minute, please. Yes. So if I ask you the electronic configuration of, let's say, palladium, so can you tell me?
It would be 4s2,
No, it's see, it's in fifth, not fourth.
5s2,
5s2, very good,
4, 4d8,
very good. In the same way, if I move over, if I talk about iridium, so it is going to be,
6s2, 5d7.
yeah. So, but usually examiner ask you the electronic configuration of these 10 from the transition, not more than these 10. Okay. So what is the electronic configuration of this? Where it is going to be end, arsenic.
Uh, 3,
Sorry,
4, 4p3.
4p3, very good. I hope it's understandable now.
Yes, sir.
Okay. So see, sometimes they ask you to label the orbitals, then me drawing the shapes, filling of orbitals like this. Okay. Then ionization energy. Here in the first class, we have discussed the ionization energy. Just we will give the quick review that it based on the formation of the cations, right? So
Yes, sir.
basically, it is the energy change when the cation is formed. So to make the cation, the gaseous, the element must be in the gaseous state. That's what we have discussed
Yes, sir.
earlier as well, because before the gaseous state, the if we provide the energy, it utilizes in its atomization, right?
Yes, sir.
Okay. And to remove the electron, we use mass spectrometer. The mass spectrometer is the one which basically provides the energy. Uh, in which we provide the energy. Uh, and that energy actually used, and as a result, the electron gets removed, and the mass spectrometer note that amount of energy. And from this spectrometer, we can turn any element into the cation, like it's not like the group 1 or group 2 or the metals. We can also do the same thing with the chlorine, and nitrogen, oxygen, the elements which usually form negatively charged ions are also used, can be turns into a positive charge ions. Is this clear?
Yes, sir.
Okay, we are done with these definitions and the examples, right? Equations.
Yes, sir.
Okay. Now the next thing that we need to discuss is the factors affecting the ionization energy. So, uh, basically, the first factor is the nuclear charge, because we are removing the electron from an atom. So if we go inside the atom, we will find that electron is basically in the atom due to the forces of attraction from the nucleus, which is holding that electron, right?
Yes, sir.
So it means that we need that much amount of energy, which actually is the greater than the force of attraction, and as a result, electron overcome the nuclear forces of attraction and comes out of the nucleus, right?
Yes, sir.
Okay. So the nuclear charge is the main factor which, you know, affect the ionization energy, because the nuclear forces of attraction are also become upon nuclear charge, and nuclear charge is dependent upon the number of protons, right? The more the number of protons, then there will be a more nuclear charge, and if there will be a more nuclear charge, then there will be a stronger forces of attraction. So the nucleus and the valence electron have stronger attraction in that case. And if this is the case, then we need a more amount of energy to remove that electron from the valence shell. And if there is a less number of protons, then there would be less charges, less nuclear charge. And if there is a next nuclear charge, then the forces of attraction would be lesser, isn't it?
Yes, sir.
And as a result, the ionization energy will be lower. We need less energy to remove that valence electron. If you have any query in it, please ask.
No, sir.
Okay.
As we move down the group, the energy decreases, but when we go to a new period, the energy increases.
Ionization, but it depends upon several factors which we are going to discuss here. Because if right now, if we just discuss this, we talk about nuclear charge, isn't it?
Yes, sir.
And what we have figured out that if the nuclear charge is higher, then the ionization energy would be
Higher.
higher. So let's have a look at the periodic table. What is the nuclear charge of sodium?
11.
11. What is the nuclear charge of potassium?
19.
19. What is the nuclear charge of rubidium?
37.
So what is happening to the nuclear charge?
It's increasing, hence the ionization energy is increasing.
Hence the ionization energy
Is increasing.
is increasing. But if you recall, you just said that down the group ionization energy.
And when down the period, the ionization energy decreases because there are more electrons and thus there's more repulsion. But down the period, the energy increases.
No, it's not down the period, it's down the group.
Okay.
It's down the group and crosses the period. So you earlier, before telling you this, what you said that down the group ionization energy
Increases.
decreases, right? You said that, right?
Yes, sir.
And that is the truth. That is true. It decreases.
Okay.
Okay. But actually, you are right now just considering this factor. And by this factor, if I apply this factor over here, so ionization energy would be increasing, but I am neglecting the other factors.
Yes.
Okay, so let's move to the other factors. Distance between the nucleus and the valence electron. The more the distance, it's I think very simple and understandable. The more the nucleus and the valence electron are away from each other, the weaker the forces of attraction between them. So the ionization energy needed to remove an electron would be lower. So the ionization energy decreases, right?
Yes, sir.
Is this understandable?
Yes.
Okay. And the third one is the shielding effect. Do you know what is shielding effect?
There are multiple shells between the valence shell and the nucleus. Thus,
And then,
it
yeah, and
we
these
can see it
electrons,
forces of attraction.
yeah, these electrons are actually shielding this electron from the nucleus. That's what we call shielding effect, right?
Yes, sir.
And the more the shielding effect will be, the ionization,
Lower the ionization energy.
the more or the lower?
More shielding effect, lower the ionization energy.
Lower the ionization energy. Is this understandable?
Yes, sir.
Okay. Okay, fourth one is the spin pair repulsion. If there is a pair of electron in one orbital of subshell of P or D only, we are not talking about S, because S has only one orbital, and when this one orbital have a pair of electron, it is completely filled, so it is the most stable, right? But in P and D, we
Yes,
have
sir.
more than one orbitals. So the electrons in this pair repel each other. As a result, the electron gets further away from the nucleus and the ionization energy decreases. This would be the only case when the valence shell has the p or d subshell.
And they are partial.
Yeah, and one of the p or d subshell is
Half filled.
one of the p or subshell p or d orbital is filled or have a pair. For example, see, this is p and this is p of another atom. In this p, there are only, this is half filled, right?
Yes, sir.
And over here, this one gets a pair. So this pair have a repulsion in it, and as a result, one of the electron gets further away, gets distance from the nucleus, and as a result, its ionization energy decreases. Is this understandable?
Yes, sir.
Okay. Now let's apply all three factors over here. What is happening from here to here and here to here in terms of nuclear charge?
The nuclear charge is increasing, but the distance from the nucleus to the valence electron is also increasing.
Okay.
And the shielding effect is also increasing, thus the ionization energy would decrease.
Very good. The ionization energy would decrease because the effect of the shielding effect and the distance both outrule or both outweigh the effect of nuclear charge. Because nuclear charge increases, what happens to the ionization energy? It increases, right? When
Yes,
distance increases, what happens to the ionization energy?
it decreases.
When shielding effect increases, what happens to the ionization energy?
It decreases.
It decreases. So all of these things are increasing down the group, right?
No,
All of these
down the group, yes.
down the group, nuclear charge is increasing, distance is increasing,
Yes.
shielding effect is increasing, right? But these two
Yes, sir.
to decrease in ionization energy, and this one only leads to increase in ionization energy. So these two are going to outrule its effect or outweigh its effect or cancel out its
Yes.
effect, which leads to decrease in ionization energy down the group. Is this understandable?
Yes, sir.
Okay, that's what we have discussed over here. Okay, I'm going to share this whole
Yes.
file with you. Then we have ionization energy trend across the period. Okay, what happens across the period? If I
The ionization,
let's have a look at nuclear charge. What happens to the nuclear charge across the period? It's
it's
increasing,
increasing.
right?
Yes.
3 to 4,
Yes.
4 to 5, 5 to 6, 6 to 7, 8, 9, 10. Okay, what happens to the distance?
Distance is increasing
Why?
because the number of electrons are increasing.
Okay, number of electrons are increasing and the nuclear charge is increasing, but the electrons increasing are actually the electrons are getting into another shell or in the same shell?
In the same shell. So it's actually remaining the same
Remaining the
throughout the
same
period.
or somewhat decreases because the nuclear charge is increasing and electrons is getting filled in the same shell. So the attraction would be stronger, which makes the elements outermost shell to be little shrinked.
Okay.
So it almost remains the same or it decreases slightly. Did you
Okay.
understand this?
Yes, sir.
If you have any confusion, you can ask.
No,
Okay, so distance is decreasing or same. What happens to the shielding effect?
it remains the same.
It remains the same, right? So see, it means these two have no effect on the ionization energy, right?
Yes.
And only nuclear charge is affecting the ionization energy. So what happens to the ionization energy? Will it increase or decrease?
It will increase.
It will increase. Very good. So just read over here. That's what we have discussed.
Okay, sir.
Any confusion till here?
No,
Okay,
it's all clear.
okay. Now, so that is the general trend. See, here I have made group period 2. So from the last first one to the last one, there is an increase in ionization energy. In period 3 as well, from first to the last one, there is general increase in ionization energy, and the reason is same. That's what we have discussed, that the nuclear charge is increasing, distance is decreasing or remains the same, shielding effect remains the same, hence the forces of attraction gets stronger and the ionization energy increases, right? But if you see
Yes,
at
sir.
2 points, there is a depth, there is a fall between the ionization energies, right?
It's because the change of orbitals, we go from S to P and P to D.
Here it's right. You are correct for this, that S2P, because P is at a little distance, so the distance increases, shielding effect slightly increases, and the ionization energy would get slower when we move from beryllium to boron and we move from magnesium to aluminum. You are perfectly right. Now, what?
And the next one is, it is the P shell is half filled.
Yeah, here very good. Its P cell is half filled, which is more stable, and here P has a one pair, which makes the electrons gets further away from the nucleus due to the spin pair repulsion, and the ionization energy decreases. Here I have discussed these reasons. Is this clear?
Yes, sir.
Okay. We have discussed about the successive ionization energies in all the last class as well, right?
Yes, sir.
Okay. So we are almost done with the thing. We have to start with mass spectrometry in the next class. And then I think after next class, we will be moving towards either moles or bonding. We are almost done with the atomic structure. Just go through this file. I'm going to share it with you after this, and you will go through and tell me if you have any queries, okay?
Okay, sir.
Okay.
Can you send me the soft copy of questions when we complete the chapter?
I think I can share the atomic structures past papers with you, because almost 75 to 80% we are done. So you can go, you can do those.
Okay, sir.
Okay. Okay. So shall we continue from here tomorrow?
Yes, sir.
Okay. Okay then. Take care. Goodbye. Allah Hafiz.
Lafas.
Allah.